Hi everybody, welcome back to this course on Internet Technologies. I'm Vardan and today we'll be studying about Secure Socket Layer. Secure Socket Layer or SSL was developed to provide security for data sent over the internet, especially when using protocols like POP3 for email retrieval, LDAP for directory services, and of course HTTP for the web. While TCP ensures reliable delivery, SSL ensures that the data remains private and intact during transmission. It does this by sitting above TCP and encapsulating the application data in a secure wrapper. SSL includes various sub-protocols, but the SSL record protocol is the core. It provides confidentiality using encryption and integrity using MACs. Now, SSL aims to achieve three major goals. First is authentication. That means both the client and the server should be sure that they're communicating with the intended party. Second is data integrity. Now, SSL ensures that the data received is the same as the data sent without unauthorized alteration. Finally, we have data confidentiality. SSL hides both the application data and protocol level information, so even details like the key exchange mechanisms or cipher types can't be spied on. SSL has two functional parts. The first part ensures security of data using SSL record protocol. It fragments, encrypts, and secures the data before it's sent over TCP. The second part consists of three sub-protocols. They are handshake, chain cipher spec, and alert protocol. These manage connection setup, cipher negotiation, key exchange, and error handling. As shown in the diagram, they sit above SSL record and below the application layer. The SSL record protocol handles the bulk of SSL's work. It takes application layer data and breaks it into fragments, no larger than 16 kilobytes. Each fragment may be optionally compressed. Then a MAC or message authentication code is appended to verify integrity. The combined data is encrypted. Then an SSL record header is added to create a record. This record is then handed to TCP for transmission. The result is an encrypted, tamper evident, neatly packaged message. Now let's see a visual breakdown of how SSL record protocol works. First, the application data is fragmented and each fragment may optionally be compressed. Then a MAC is added for integrity. Then the data with the MAC is encrypted. Finally, we add an SSL header and the resulting secure record is what gets passed to TCP. This layered structure ensures the data is not just encrypted but also verifiable and efficiently handled. And at the receiver's end, this process just reverses. Each SSL record starts with a small but important header. It contains content type, which tells what the type of content is. It could be a higher level SSL sub protocol like handshake, or it could be HTTP data or some other application's data. Then major and minor version numbers of SSL, let's say 3.1 for TLS 1.0, and the length of the payload. This helps the receiver know how to interpret the incoming data and how much of it is to be read. The alert protocol is used for reporting errors and other session events. Each alert has two bytes, one for severity, that could be one meaning warning, two meaning fatal, and if it's fatal, the session terminates. And the other byte is for specific error code like unknown certificate or bad MAC. The chain cipher spec protocol is very simple, just a single byte of value 1. It acts like a trigger, informing the other party that all further messages will be encrypted using the agreed upon keys and algorithms. It's sent by both client and server before secure communication begins. And the SSL handshake protocol is where the secure session begins. The client starts with the client hello, which include the supported SSL version, a random number, a proposed session ID, and a list of supported cipher suites. A server replies with a server hello, echoing or selecting these parameters. It may also send its certificate for authentication and request client certificate for authentication on this side. Then key exchange occurs via RSA or Diffie-Hellman. And once both parties agree on keys and authentication, they each send a change cipher spec message and a finish message to indicate the secure session is ready. Let's walk through this handshake sequence. The client hello is sent and the server hello is received in response. And in the second part, the server send its certificate and it may request the client certificate and send the server key exchange data. The client replies with its certificate and key exchange details. Finally, both sides send change cipher spec and finished messages. At the end of this handshake, both sides are authenticated, a shared secret has been agreed upon, and encrypted communication can now begin. And that's the end of this video. And the next lesson will be about transport layer security. So, thank you for joining in, and I'll see you next time.